So we already had fantastic talk this morning on PFM. So let's change a bit topic using a piezoelectric sample such as PZT to illustrate some point of this tutorial. So the idea is to take advantage of both an arbitrary waveform generator and a lock-in amplifier in the UHFLI, and then combine it with a FlexAFM. So clearly, none of these tutorials could have happened without the great help and commitment from both Mehdi Alem and Kivansh Esat. So Mehdi, you will see him this afternoon. Kivansh, you just saw him in the video of the KPFM video. And so we could not meet physically and had to do everything remotely, which is an additional challenge. But yeah, we enjoy this teamwork effort. And while struggling to make everything work, we also felt a little bit closer to what our customers are experiencing every day. So, and I guess that's what we want to see in a tutorial too. But first of all, please let me start with a message of praise to our customers. So I don't want to spoil the image contest that we'll address at the end of the day, but could not resist sharing some of the beautiful contribution from our customers. So here we see some high resolution images that we could certainly not achieve ourselves because it requires expertise not only in electronics and control, but in many different aspects where everything must work together. So these are images from companies such as Nanosurf, Nanovision, Park System, IBM Research in Europe, in many different modes such as Kelvin probe, Piezoresponse Force Microscopy, and even scanning thermal microscopy. So from our side at Zurich Instruments, most of what we show are usually simple loop back from output to input or with simple resonator. So these are very humbling experience for us, but also great motivation to help everyone optimize the system and push the limit of resolution on their machine. So with this in mind, I hope to contribute on my level on some of the specific mode and technique that can be achieved with our instrument. So let's dive into this tutorial, which is going to be cut into 3 parts. So the first one is we were thinking about a way to illustrate the arbitrary waveform generator in the context of SPM and to synchronize it with CAN, to have more waveform generation, and to make it a bit more exciting. We wanted to write and read on the same image, so basically between trace and retrace. And then because we are addressing this piezoelectric force microscopy, then we have to talk about resonance tracking enhancement method and PID optimization related to DFRT. And probably the more interesting part of this tutorial will be the switching spectroscopy PFM. So at the end, so to apply in concrete terms some arbitrary voltage ramp, eventually some delay, and some time resolution consideration. So in terms of how we connect everything, so we usually start with some breakout module, signal access module, or some breakout box, so to connect between the UHFLI and the microscope, and so that they can talk to each other. So typically you have some line trigger, or maybe I could have used the laser pointer here. So you can have the line trigger here that is fed into the DIO trigger. Then because here we are using a UHFLI now, not an HF2, so we don't have an adder. So we just took the simple route of outputting the AWG directly on the aux output DC that is sent to the tip bias, and we excite the AC to the sample bias directly. At the same time, since we have 2 inputs, we can measure both lateral and vertical deflection, but most of what we saw are on the vertical deflection. On the Nanosurf FlexAFM part, so this is basically contact mode, so it's a fairly basic. So what we were doing is mostly a soft, a smooth landing for the tip to have a Z feedback and then to do topography in contact mode. In terms of tip and sample, so we had a customer kind enough to let us a PZT, and actually realize only fairly recently that it's a 3 monolayer PZT with this ratio of 20/80, and then we just seal the pane to contact to the bias. For the tip, we used the standard tip for electrical measurements. So EFM, even though it's more usually for dynamical like PFM technique, because normally for contact mode, you want to have something very soft so that you don't wear off the coating. But since you are also doing dynamical mode with this cantilevers that is clamped at both ends, so we can't have something too floppy, otherwise we don't have a good contact. So that's kind of the trade-off. Okay, so in terms of, so what makes a good arbitrary waveform generator, especially compared to a pulse generator? So if you just look here at this picture, you see that you are basically only generating pulses, but it's all about timing. And so an AWG, it's about generating on the output the right sample at the right time, and then to kind of orchestrate everything with all the equipment that you need to acquire the data. So for the AWG built in the UHFLI, so we have actually 6 output because you have 2 signal output, the fast signal output that you usually use for modulation, and then we can also drive from aux output directly. Because it has a lot of marker and triggers, so it's easy to synchronize with CANengine, with third party, but also with internal signal from the DAC. And of course, it's a very generic and arbitrary waveform, so you can play any type of preloaded waveform or chip or excite the full frequency band, so control the delay for time resolution, or if you really want to just draw your function sample by sample, you can even just load what you want and it will play. Of course, so this flexibility comes with a bit of complexity, and so it's usually a bit more complex to use than standard function or pulse generator, and also because you have a fairly high bandwidth, so it's sample at 1.8 giga sample, so it's limited to 1.5 volt on the signal output, but it can go up to plus minus 10 volt on the auxiliary output, but then limited to 5 megahertz. Okay, so how do we apply now this AWG for SPM? So let's start from the AFM controller. So we start our scan, we have a feedback, then at the end of the line, we send a trigger. From this trigger, now everything is controlled from the AWG, which starts to write its pattern, so whatever you want him to do. And then basically halfway there, it will send himself another trigger, let's say to the DAC for recording or for changing some other parameter within the lock-in environment, such as the AC drive for the lock-in on off. And then on the barcode is just either. And then the DAC is just following instruction and then recording the channels, aligning on a grid as we know it. So typically when you make the image, if you just look at the piezo response phase, then of course you have nothing on the forward because at that time it's a pure DC, it's only writing, and so there is no measuring. But then on the barcode scan, then we see exactly what has just been written the line before. Or I mean, not even the line before, but the forward before. Okay, so let's see now how does this look like in some of these terms. So if I turn it on, this stuff, yeah. I have to remove the laser pointer so that I can eventually stop. So that's a video graph from the Lab1 interface. So we started with a minus 10 volt DC offset, and the reason is because we wanted to start with something very flat so that you see that there was nothing written before. Then we load our AWG program. So we'll go back to that a bit later. So, but let's just pause here for a sec and to show here so some additional features that we can feed inside the program, such as the signal output that you see here and to be enabled. So here it's 0, so that corresponds to signal output 1. So the number 2 here, and it's basically off. And then eventually you turn it back on again on the retrace. And of course here, nothing happened until you get the trigger from the AFM, so which start, so it's at a weight digital trigger, and you see that there's no state enabled here. So all this stuff, and of course you can create the loop and put some logic, some conditions, and then when you run it, then it's available on the aux output because we have played on the aux wave output here. So we just have now to select AWG, and now we don't have, it's not controlled by the offset, it's controlled by the AWG. We've done everything from 0 to 1 volt, so we just blow up the scale to make sure we can write with 10 volt. So now we move to the Nanosurf software. So we just have, standard topography. So we see the topography going forward here. Of course, backward would be the same. But then as the image is building up, you see that there is nothing on the forward because this is, as we said, pure DC. And on the backward, it is pure AC. So we really are only writing in this part and then reading in this other part. So let's move a little bit fast forward in this stuff. And here, yeah, okay, let me pause again because halfway there, so we can also see what's going on with the AWG. And precisely here, you see, for instance, that the trigger is enabled, and now the output is automatically enabled and is actually switching back and forth from the AWG while it's scanning. So we get the trigger from the line, which gets started, and then we changes the AC. And so that's exactly what you see. And if we get until the end of the line on the image, so we see the image building up as I have shown you in the previous slide. And if I just go a little bit down, so now we basically turn the AWG off because we want to convince ourselves that we did write everything and we have the same between forward and backward. So in this case, now there is no more AWG involved. It's just a standard static PFM, and we just go downward. And if you start to also build up the image, you see that forward and backward are obviously exactly the same, and we are exactly on top of what we had just written on the previous scan. So here we were actually making a little bit the mistake of driving a bit too hard with 1 volt AC, which we found out when doing the SSPFM that this is also doing some switching already at this voltage. So that's why that second image is a bit less nice, but you see exactly the same pattern on both sides. Okay, so let's finish that part and then continue and move on to the next section. So on Piezoresponse Force Microscopy. And so of course, the challenge with PFM is that we cannot rely on a PLL because you cannot, because the phase is flipping depending on the polarization. And therefore, you cannot rely on the phase, but you have to rely on the amplitude only. And that's why you use this amplitude modulation technique. So, so an amplitude modulation is basically what you see here. So you have inside the carrier, and so this carrier will be typically your cantilever oscillating. And on top of that, you have the envelope that is modulated of this carrier on the two sides. So you have actually three terms. So you have this frequency inside, you have this frequency up, and then you have this frequency down. So you have these two sidebands, and that's what you see now. And you can demodulate on the HF2 or on the UHF because you have several demodulators, and both for in-plane and out of plane. Out of these two sideband amplitude, you basically subtract them and then feed them into a PID. And then, so this PID will act on the center frequency, which can be the cantilever frequency or the carrier frequency, as you want to call it. And that will basically center everything to make the sidebands move around the resonance. If you actually plot this resonance as a function of voltage, so a so-called open loop transfer function. So before we close the loop, we see here that this is not the phase. This is a difference of sideband amplitude, but you see that it has a nice monotonic linear behavior exactly as a resonance. And so that's what we can feed now into, that's what we feed into PID. So it's basically now back to square one, where we doing the same as a PLL, but with a difference of amplitude. So now we are feeding this D mod 3 minus D mod 2 instead of feeding the phase. Okay, but that theoretically, this is very easy to understand, but of course, it's to put it into practice and to have a nice workflow. And that's where the Lab1 user interface is very convenient because you understand every step, you can measure all the parameters and you can optimize all the feedback. But usually it always starts with a sweeper. So you have to get this contact resonance. So this is not the first eigenmode, so it's not in the free resonance, but it's in the clamp resonance. So it's typically 4.4 times F0, then you can measure the contact resonance, the full width at half maximum, and then you enter with this amplitude modulation scheme, where for the carrier, you use the contact resonance, and the modulation, you just make it symmetric around this contact resonance to measure it. And then you can sweep again, measure the response that you can then feed into this PID. So the PID, and this PID comes with the PID advisor, where we enter the gain. And the last parameter that is actually in the hand of the user is the target bandwidth, which is typically 1 over pixel dwell time. And of course, for the PID to do its job well, it has to be fed with the lock-in data that is, of course, measured faster than this, and that typically a couple of times faster than this target bandwidth. Then you see everything in the plotter and so on. Actually, I don't want to spend too much time on this because we have had a nice tutorial from last year user meeting that you can find on Zurich Instruments YouTube channel. So you actually see here what the equivalent of a contact resonance would be, what each sidebands at positive and negative sign would be, and then the difference when you subtract R3 minus R2, typically, and with the nice slope that you use for the PID. And also, I don't want to spoil the very nice tutorial from Mary and David this afternoon, which not only is going to show DFRT on the vertical deflection, but on the lateral deflection simultaneously, and recording all that with a Bruker microscope. So please join them for this afternoon. So now let's move to the last section of these tutorials, which is about switching spectroscopy PFM. So the reason we picked this example with this PZT is that to some extent it's look a little bit like a pump probe experiment. So here you are not having a laser pump tone. So it's not an optical pump probe, it's really an electrical pump probe where you reverse the polarization by applying an electric field, but then you don't want to measure right away or when you are pulling the field or pulling the polarization, but after that. So all the measurements, you want to do them basically where DC is 0, and it's just a pure AC measurement. So it's a little bit like when you were writing and reading in the AFM and in our imaging before. The writing is DC, the reading is AC. And so now you can basically sweep your voltage ramp from, let's say, minus 10 volt to plus 10 volt and then back again. And then you start to see this hysteresis effect, which means that you have some non-zero remnant field where you have where you still have some bias voltage before you switch everything back again. Okay, so in terms of making this, so let's focus a little bit on the sequencer, so from the AWG, and so you can look at it as a window into the FPGA. So basically, you can really code what you want in a very deterministic manner, and then compile it, and then run this on the instrument directly. So you can have a very deterministic control of all the timing happening, and then you can even play some logic. You can have you can set some trigger within the AWG to synchronize other part of the Lab1 environment. And then, of course, here, for instance, you can play directly on the aux output or on the signal output. So in this way, so even if you want to make a long sequence where you need to repeat a lot, because typically for pump probe measurement, you often need to repeat the measurement a lot of time because otherwise the signal is too small. So you don't need to code everything one after the other and then having a different delay. You can just have a while loop, for instance. And also what is nice is that this AWG is now embedded into this complete Lab1 environment. So that means that you don't need to code the oscillator yourself. This is already done. That's what you use already for the lock-in. You can just add it on the output of the AWG, and then you get the equivalent of a waveform like this. Okay, so now let's illustrate how this would work again with inside the Lab1 user interface. So I just want to remove the pointer here. And so, so we have loaded again our AWG program. You have a lot of constant because there is a lot of parameters that we can play with. And of course, we don't want to change. So we can just change a constant when you want to change a parameter. So that's very easy. And let me have a quick pause here. So to emphasize maybe on the way we have we set the trigger. So within the loop that we define, so we have up to 32 digital trigger, but here we are just using, let's say, the first one and the second one, so DIO0 and DIO1, the one that are also available on the front panel of the UHF. And that's what we use now to synchronize everything else. So while we generate these patterns that we can now check on the scope, so for clarity, we just do it now with a few pulses so that we can really see what's going on and what we control. So let me also just have a small pause here. I didn't want it to do that, but yeah. So if we just, yeah, so here you see that we have the first trigger, so the one coming from AWG trigger 1, and that corresponds yeah, to about 1 second for in this case, where you start at -10 volt up to +10 volt and then back again. And so that's the one you can use to trigger, for instance, the acquisition of the DAC. But at the same time, you can have a second trigger, so also coming from the AWG, and now you can start to look more inside, and then I can also pause a little bit, where you see that we have that works as a gating trigger. So after every pulse that you have submitted, then you can have a certain dwell time, a certain window, and then you start to measure only after that part. Of course, for switching spectroscopy, it's kind of for always a static delay, but you can think of having a sweeping of delay as a next step. So this gating trigger, that's the one we are going to use now as a second step. But let's look how the data looks like. So when the AWG is on, so we start to see now basically this sweeping back and forth. So we see the amplitude and phase flipping between 280 degrees. When we turn the AWG off, nothing happened. So we are not using a sweeper, we are using the AWG directly to sweep the bias voltage. And here we have shown everything with basically 10 steps for every part of the sequence. So let's increase the number of step size to have a bit more points, of course, to make things a little bit longer as well. So now you see that we have a longer sweep, and so that we can synchronize with the data acquisition. So in the data acquisition, we use AWG trigger to start the recording. First of all, we do it just in continuous mode. So in this case, we just have the everything stream for the acquisition. So we see our phase reversal of the phase. And then in the grid, you see that we've used basically 2014 column. We have used it in, so let me just pause. Yeah, we have used four rows. So we can, of course, average it as much as you want. And we used it as bidirectional. So bidirectional is like every second trigger is flipping so that we can see a little bit some of the hysteresis effect. But of course, what we are interested in is not this continuous mode, but this triggered mode. And so for this, we need to trigger the acquisition of the lock-in itself. So for this, we use the trigger, AWG trigger 2, and we record data only when the trigger is on high at the rate that we specified here. And then we can start again the acquisition. So in this case, we now have two triggers, one to trigger the DAC and one to trigger the lock-in that within the DAC is going to capture only, let's say, within this gating trigger or gating window. So we have removed the other trace for visibility. And now if you look at the buildup of the spectroscopy, let's say, into the data acquisition, you see that it is not continuous anymore. We just have these strips of data. So here it's now the amplitude and not the phase. And if you look in the scope how it looks like, So everything, so it's a low sampling rate because you have a lot of data that we want, lot of data points that we want to show. And if we zoom, and let me pause one last time here. So basically this gating trigger here corresponds to one of these data captures there. So we have a very nice match between what you write and what you read again. Okay, so I think, so to summarize that part, and of course, to also show the hysteresis curve plotted into a nicer way here. So we see the 180-degree phase reversal. We see a small hysteresis around this with 1 volt for this sample, which is also the reason why applying 1 volt AC was not a good idea for this sample. And then we also show how to acquire data both continuously and in a triggered fashion. And because with this gating trigger, now we can synchronize all the lock-in measurement, and that is, of course, all totally configurable. So we've shown you this basically on one point on the surface, on a PZT, for rather simple scales. But now, of course, the next step would be that you can, of course, play with the width, with the delay, with the dwell time, and all these things. So, of course, then, for instance, you can do this POM probe, where the polarization, so you can, of course, vary the amplitude, you can vary the width, and you can also vary the delay between the pump and the probe. So going back now to a time resolve. But basically, everything that we have shown works the same way if you just introduce this delay too. Okay, so let's jump to conclusion. So I hope I could convince you that an arbitrary waveform generator is a great addition to lock-in detection. So not only is it useful for controlling the experiment, but also the measurement and to synchronize everything from the same box. And actually, it was also great to see the talks, let's say from Benjamin, where we see how he made he had a rather complex experiment with a lot of different tools. He had to use OPA to combine the oscillator and stuff like that. So of course, and in this case here, you just have one box. It does it all, because you have the lock-in, you have the AWG, you have the triggers, and you just synchronize it with your scan engine or with your grid when you start to go pixel by pixel. At the same time, you are within a nice, comfortable, and hopefully familiar environment that you have used already for all these resonance enhancement technique. So this remains the same, it's just on top. And then the UHFLI on top of, let's say, HF2LI or MFLI is basically time resolved because it has much higher sampling rate. You can do this time measurement. You can also have a digitizer if you want. So it really opens up more possibilities. And the last point is actually a personal take-home message. I think it's way more interesting for us to test these new modes with our customers than with ourselves, because I think it would make our lives easier too. So with this, so I hope you find this useful. Let me check the time. I'm slightly ahead of schedule, but I think, I think it's good. I would, of course, strongly encourage you to send us a question if you have related to this question. But I think probably now the best is to move on, to stay on schedule and to move on to the roundtable.